Okay, we have here 26 participants, and we can start. Oh, hi,
Okay.
Hi.
Hi, nice to hear you.
So we can start our seminar now.
Okay, Andrew, thank you very much. Thank you very much for the invitation to talk. I've just switched off my video because I think that probably helps with the bandwidth connection. Please interrupt if obviously anything goes wrong. So, as we were just discussing before the talk started, there are a number of talks in this, or there have been two talks in this seminar series, one by Professor Rubtsov, one by our PhD student, Roberto Donofrio, which have touched on Monge Ampere geometry and applications in certain geophysical models of fluid flow. And really the aim of my talk today, which is going to be very much a colloquial, a colloquium style talk, will be to give the sort of broader background to some of the problems in fluid mechanics that have led to the stream of research that we've been doing, and hopefully later in the year, subject to conversations with colleagues, there will be two further talks on research that is currently underway in this area, and I shall refer to that as we go along. So this is really very much, as I say, a sort of applications talk. There's going to be some history as well as some discussion of more contemporary research. So, there we go. So the basic plan is that I want to talk about the Euler and the Navier-Stokes equations and talk about these in the context of the problem of weather forecasting. And more particularly in how we study solutions of these equations that focus primarily on the nature of vortex motion. I will then move on and discuss the semi-geostrophic equations, which is something that was central to the talk by Roberto a few weeks ago, and really sort of show how some of the geometry inherent in those equations has underpinned methods, numerical methods of solution, and the relevance of this to studying problems in atmospheric dynamics. And then the last part of the talk, I'll move more on to the things that we've been doing more recently involving applications of Monge Ampere geometry. So that's a very broad plan. So I'm going to start with really what is the mathematics of weather? The problem of weather forecasting is basically solving 7 nonlinear equations, partial differential equations, in 7 unknowns. And these equations are, there's an equation for the conservation of mass, or the continuity equation, an equation of state relating pressure, density, and temperature, Newton's second law of motion for a fluid, which is basically 3 equations for the wind speed and direction. And these equations, of course, include a representation of the Coriolis effect, which is very important when looking at fluid motion on a rotating planet. The first law of thermodynamics, or conservation of thermal energy. And finally, there's an equation for the conservation of total water content. So weather prediction and indeed climate modeling is based very much on solving these 7 equations in 7 unknowns. And it's an initial value problem. So you start with observations of the atmosphere taken from a variety of observing platforms. One might think that with satellite coverage now, we have pretty much sort of global coverage of weather phenomena. But a big problem is the fact that we still have insufficient data to initialize a forecast. For example, a satellite can't really see what's happening underneath a cloud, and that's very important from the point of view of the weather that's going on in certain localities. So the problem really is actually blending observations of the current state of the atmosphere with a previous forecast. So you're sort of updating a previous forecast with new information. And then the numerical model, of course, it solves these 7 basic equations in 7 unknowns, but it has to represent a lot of processes within the atmosphere, heat exchange, momentum exchange. There's representation of certain important aspects of atmospheric chemistry, obviously radiation models, things like this. So it very quickly becomes a highly sophisticated numerical model. And typically these models are solved on supercomputers. The global models now have actually quite a fine resolution. So you're talking about a horizontal separation of grid points of the order of 10 kilometers. And very often several hundred levels in the vertical. And at each grid point, you're calculating your 7 basic unknowns. So a quick calculation tells you that you're really solving for about 10 to the 8 unknowns. And from the basic variables such as wind speed, temperature, pressure, you derive things like cloud and precipitation. So that's the sort of modern view of what's going on behind weather forecasting. Obviously, what I want to do now is to sort of go behind the scenes, as it were, and look a little bit more carefully at what are the really important ideas that underpin this in terms of the mathematics. And to do that, one really just has to go back to where it all started. And it was this guy, Wilhelm Bjerknes, Norwegian mathematician, who actually in the latter part of the 19th century was working with his father, studying the motion of hypothetical vortices in the ether. So they were very involved in studying the ether. This, of course, was pre-special relativity. And it was during their studies of the ether that they started to think about certain problems in vortex motion, and Bjerknes realized that he could extend these ideas and look at some problems in actually calculating weather. And his breakthrough really came by focusing on the circulation theorem. So the basic quantities here are the notion of circulation, which is a macroscopic measure of the rotation of a fluid. So it's given by a contour integral of the fluid velocity around some closed curve. By Stokes's theorem, we can relate this to the vorticity of the flow. So the vorticity is the curl of the velocity vector. And using the equations of motion, you can calculate the rate of change of circulation of a fluid. And you'll have to excuse the slightly odd notation here, but I'm going back to Bjerknes's original paper. So the density of the fluid, we normally denote by the Greek letter rho. K is just the reciprocal of density. And then you've got these vectors, which are the gradients of K and the gradients of the pressure field B and G. And basically the calculation says that if these gradients of density and gradients of pressure are not aligned, then you will generate a change in circulation. So at this point, Bjerknes knew about most of the maths and physics that went behind computing, weather on the globe. And of course, what he realized was that you were never going to be able to do that in any analytic sense. But he also realized that by using things like the circulation theorem, you could actually deduce important physical phenomena using some very simple ideas. And his first application was to the so-called sea breeze effect. So this is the figure from Bjerknes's 1898 paper. And what you've got is that you've got the horizontal dash lines are surfaces of constant pressure, and G is the vector, it's the gradient of pressure. Now remember that pressure decreases as one ascends in the atmosphere, and G was minus the gradient of pressure, which is why it's pointing vertically. And then the solid lines that slope and are not necessarily parallel to the pressure surfaces, these are the lines of constant density. And this problem here is one where you have, to the left of the picture, you have an area over the ocean. To the right of the picture, you have an area over land. And typically on a summer's day, the land will heat up more rapidly than the ocean. So over the land, the isolines of pressure and density will no longer coincide. There will be a gradient, warm air will rise. And what the circulation theorem tells you is that in these conditions, a positive contribution to circulation is generated with cooler air being drawn off the sea. It rises over the land and returns at higher levels. And this is the classic sea breeze effect. Now, this is all well known to us, but of course one has to remember that 150 odd years ago, when they were really just beginning to understand thermodynamics properly, the work of Carnot and Joule and so on, to be able to quantify something like this using something like the circulation principle was a massive step forward. And Bjerknes sort of really took this on as a way that one might be able to make progress in computing flows related to, you know, the circulation of the atmosphere and the ocean using the laws of physics. And this really is the first time that they're going to appreciate that circulation or vortex motion is, on the whole, one of the things you really want to focus on. So we all know this. We know that we have hurricanes. That's the top left picture approaching the Caribbean. We have tornadoes, the bottom left picture, or waterspouts. Vortices are observed in other planetary atmospheres such as Jupiter, and of course you observe them, you know, in the home. So vortex motion is a ubiquitous feature of fluid dynamics. It's a very important one. And of course, now it can also be studied using numerical techniques. So what we have here, the top left, is a representation of what we call the polar vortex. So this is actually a plot of a thermodynamic quantity on a surface of constant vorticity. And this sort of thing is important in studying things like the ozone hole. On the top right, you have a picture of vortex motion in two-dimensional incompressible flow. So the red and the blue almost axisymmetric blobs show fluid swirling in opposite directions. And a characteristic of 2D turbulence is that vorticity tends to accumulate in these almost axisymmetric structures. And I'll say much more about that later. And then modern computer technology now allows us to study the turbulence in three-dimensional flows, which of course is a very different problem from 2 dimensions. And although turbulence is something that very often one can only study statistically, there's a lot of evidence coming from careful laboratory experiments and also from numerical simulation that despite the fact that turbulence is highly complicated, it's typically composed of some very basic structures, which are so-called vortex tubes. And this has been something coined by Keith Moffat at Cambridge, that these tubes are like the sinews of turbulence. But what we don't have a very good understanding of, a very thorough understanding of, is why should vortex structures be ubiquitous. It's very difficult to deduce this just by looking at the equations of motion, you know, themselves, and investigating the ubiquity of vortex motion is something that's been very important to my work with Rubtsov and others. This is just an example of a lab experiment, which this is quite recent work in Chicago, where they've been looking at the generation of vortex knots and vortex rings. This is generated by by putting tracers in a fluid and then removing a hydrofoil of a particular shape very quickly. And these vortex tubes can also develop quite interesting topologies. This is another subject that I don't really have time to talk about today. But again, it just indicates that there's a lot of structure there that we still actually have a relatively incomplete understanding of. Just whilst I'm on, before I move on to looking at fluid mechanical models in more detail, I thought it might be nice to sort of show this to just drive home the relevance and the importance of vortex motion in the atmosphere. Now, what this chart shows is that so this is the Caribbean, this is Florida, this is the eastern seaboard of the United States. This is October 2013, and what you have here are the forecasts, the simulations of what became known as Hurricane Sandy, which did the highly unusual thing of originating in the Caribbean, but making landfall in New Jersey. And the forecast of this hurricane, its track, turned out to be a great success of forecasting. So what you're seeing here is each one of these lines with different colors is the simulated track of the hurricane over a number of days. And each individual line is an individual forecast. And these forecasts start from slightly different initial conditions. So this is what we call an ensemble of forecasts. It's something that's routinely used now in weather forecasting agencies because of chaos, because of uncertainty and unpredictability. Rather than running a single deterministic forecast, you run many forecasts and look at how these forecasts evolve. And obviously, if they all evolve to a very similar picture, then there's some confidence in your long-term prediction. If the predictions diverge, then clearly the situation you're facing is much more uncertain. And in this model, what it shows very clearly is that the majority of these forecasts are predicting a storm track which will make landfall in New Jersey. Very few of the forecasts have the hurricane doing the more typical thing, which is going out into mid-Atlantic. And the reason that this forecast, and therefore that the prediction of a severe storm in the New Jersey area, which was issued in good time and actually saved lives, the reason that this forecast was so accurate was that the vortex structure, which was the hurricane, was actually interacting with another vortex, which isn't represented on this diagram, which originated over Alaska about the time that this vortex formed in the Caribbean. And the weather system over Alaska sort of progressed eastwards over Hudson Bay and over northern Canada. It was a very much large-scale structure, but its structure as a vortex interacted with that of Sandy. And what the numerical model was doing was getting this vortex interaction just right. So if you get the big picture wrong, if there'd been an error in the simulation of this much larger scale vortex, then you probably wouldn't have got the forecast of the hurricane as accurately as one did. So getting vortex motion right is a really important thing from the point of view of weather prediction. And just a little bit of shameless advertising. I've written a book about this and the sort of maths behind it with my co-author John Norbury, published by Princeton University Press. And also, a few years ago, for the London Mathematical Society 150th anniversary, I was asked to write a piece for them on the impact of mathematics on weather prediction. This is available on the London Mathematical Society website, and really talks about how contemporary mathematics has shaped and is shaping the development of weather and climate modeling. So let's now turn to things that are a bit more specific. And I've talked a lot about vortices and vortex motion, but if you ask a fluid dynamicist what is a vortex, then actually there isn't a single answer. And maybe this will become clear in the slides that follow. So let's take as our starting point the incompressible Navier-Stokes equations. It can be in 2 or 3 dimensions. There are some differences, important differences between the two. So what we have here is the time derivative of the velocity vector field u. We have the nonlinear so-called advection term where u is transported by itself. We're making the assumption of incompressibility, and therefore density, if it starts out to be uniform, will remain uniform. So the density can be sort of hidden from view. It can be set equal to 1 if you're assuming incompressibility. P is pressure, so this is the pressure gradient term, and nu is the viscosity of the flow. So if nu is 0, we have the Euler equations. If nu is non-zero, we have Navier-Stokes, and the continuity equation or conservational mass reduces to the divergence free condition on the velocity vector field. So vorticity, as I mentioned earlier, is the curl of the velocity vector field, and you can write down an equation for the evolution of vorticity. With the definition of the standard Lagrangian derivative, the big D by dt in fluid mechanics, the transport of vorticity is modified by what's called the vortex stretching vector. And if you're looking at Navier-Stokes, there's a contribution to that from viscosity. If you're looking at 2-dimensional flow, then vorticity is just a scalar. It's in the vertical direction, it's perpendicular to the flow, and therefore this term, if u is horizontal, this term will be 0, and if you're looking at Euler rather than Navier-Stokes, this term is 0. So in 2-dimensional flows, the Lagrangian transport of vorticity vanishes, and it's called a frozen-in quantity to the vector field. Now, that's vorticity, but it doesn't actually sort of tell us what a vortex is. And there are different ways of arriving at some criteria for when vorticity is accumulating and you have something that you might call a vortex. So if you take the divergence free, so if you take the divergence of the momentum equation, then let's for the moment assume that if you take the divergence of the momentum equation, then the divergence of this term, the divergence of this term will vanish because of incompressibility. So you're left with a Laplacian of pressure and then the divergence of this nonlinear term. And using the divergence free condition, you can write the resulting equation, which no longer contains a time derivative. And you deduce that the Laplacian of pressure is determined by this nonlinear combination of the gradients. So the comma here is partial derivative, the gradients of the velocity field. Now, let's just, we're going to focus on this equation for a while. But I want to start by just looking at what happens when we restrict ourselves to just 2 dimensions. So if you've got incompressible flow in 2 dimensions, you can represent the velocity vector field in terms of the gradients of a scalar, psi, which is known as the stream function. So taking the divergence of this trivially gives 0, satisfies the divergence free condition. And if we substitute this vector field into the right-hand side of this equation, then we can rearrange it so that the Laplacian of pressure is proportional to this Hessian term involving the second derivatives of the stream function. And what it turns out is that the sign of Laplacian of pressure, whether this term is positive or negative, can be related to whether you have a vortex or not. And that sort of becomes apparent when one is looking at so this is the picture of 2D turbulence, where I said vorticity tends to accumulate in almost axisymmetric swirls. What you have within the red and the blue regions here is you have vorticity is basically dominating over other type of fluid motion, and the right-hand side of that Poisson equation for the pressure, the Hessian term, that will be positive. Now, we know if we think about the graph of the stream function as a graph in three dimensions, we can calculate its Gaussian curvature, and the determinant of the Hessian, when that's positive, then that graph has positive Gaussian curvature. And the streamlines are obtained by taking level sets of the stream function psi. And so when the graph has positive Gaussian curvature, those level sets will be convex curves. And this goes some way then to explaining why when Laplacian pressure is positive, you see these almost axisymmetric accumulations of vorticity, because the individual streamlines will essentially be convex curves around some stationary fixed point. So one can see the emergence of sort of geometrical ideas in understanding what vorticity is, and one can extend this to three-dimensional flows. One doesn't need to think just in terms of incompressible 2D flow. And the Uij, this is just now is recognized as the velocity gradient tensor. So we can split it into its symmetric and antisymmetric parts. And essentially, the vorticity is derived from the antisymmetric part of the velocity gradient tensor. And the velocity gradient tensor, if it's in 3 dimensions, it has 3 invariants with regard to the orientation of the coordinate axes. And the second invariant can be written in this form, label it Q. And it turns out that this is precisely the right-hand side of the Poisson equation for the pressure, up to a numerical factor. And what this is in terms of the fluid flow is that it's the vorticity squared minus the strain, the trace of the rate of strain squared. So straining motion is something that tends to disrupt vortices. The accumulation of vorticity is something that tends to reinforce vortices. So if we go back to this picture, what we're seeing here is we're seeing vorticity here in the red, in the blue. It's dominating over the strain. In between the two, the strain tends to disrupt the motion. So the value of the Laplacian pressure here will be approaching 0. It could even be negative if this is dominating. And of course, what's implicit to all this is that in 2 dimensions, certainly we've got some sort of Monge Ampere type relation between Laplacian pressure and the nonlinear Hessian operator of the stream function. And it turns out that when Laplacian pressure is positive, when vorticity is dominating over strain, this Monge Ampere equation, a Monge Ampere equation for the stream function, is elliptic. And when strain dominates over vorticity, it's hyperbolic. So this has been captured in something that's now known in the literature as the Jacobo-Weiss criterion. Now, in the atmosphere, there are 2. Rotation is very important, as is so-called stratification. So this satellite image of a hurricane really shows, it emphasizes 2 things. One is that clearly this flow is dominated by rotation around the eye of the storm. The second thing is if we look across the atmosphere, the direction of the satellite view, then what we see, what we get a feeling for is the atmosphere can actually be thought of as a very thin layer of fluid surrounding the Earth. So in terms of weather, most of weather occurs in the bottom sort of 10 to 15 kilometers of the atmosphere. And this is what you see as this sort of blue hue contrasted against the higher atmosphere, the stratosphere, and the ionosphere, above it. And of course, the radius of the Earth is of the order of 6,000 kilometers. The depth of the troposphere, where weather occurs, is about 10 to 15 kilometers. So this just reinforces the fact that actually stratification is also really important. The atmosphere can be approximated as a very thin shell of fluid surrounding the rotating Earth. And this means that stratification and what is known as geostrophic balance really dominates in the atmosphere. So geostrophic balance is the idea that the principal motion in the atmosphere, the wind speed and direction, is governed largely by the pressure gradient. But it's done so in a way that involves this vector cross product. So this is the Coriolis term in the Euler equations for a 3D fluid. So V is just the horizontal components of the velocity. The Coriolis effect impacts on those dynamics, and what these numbers indicate is that if you do a scale analysis and you put in typical values of the horizontal wind field, typical values of the pressure gradient, then these acceleration terms are of an order 10 greater than the actual inertial acceleration of the flow. And what this tells us is the well-known thing that typically in the atmosphere, the motion is typically parallel to surfaces of constant pressure rather than perpendicular to them. So fluid is accelerating around the center of low pressure rather than going from centers of low pressure to centers of high pressure. And because of the shallowness of the atmosphere, fluid dynamicists often use the so-called shallow water equations as a simple model to study atmospheric motion. So this is a set of coupled nonlinear partial differential equations in three unknowns. So the three unknowns are now the two components, U and V, of the velocity field of the fluid. H is the depth of the fluid. G is the acceleration due to gravity. And F here represents the Coriolis parameter. So this is something that if phi is latitude, it's 0 at the equator. It's just equal to the rotation of the Earth when you're at the pole. And you also have the conservation of mass. You do not necessarily need to make the incompressibility condition, which would mean that this term is 0. The divergence is 0. The full shallow water equations don't necessarily make that approximation. But if you combine these three equations and you compute the vorticity equation for this set, just as I mentioned the vorticity equation earlier, the vorticity equation now looks like this. So it introduces this notion of total or absolute vorticity, which is the sum of the local vorticity. So zeta here is just again the cross gradient of the velocity vector. But now you think of this Coriolis term as a contribution to the vorticity, and so you can write an equation now for the evolution of total vorticity, and that is effectively controlled by the non-divergence of the horizontal wind field. So you can make the approximation in the atmosphere. Let's consider a much simpler model where actually we assume div V is 0, in which case this then becomes a Lagrangian conserved quantity. And you can use this as a very simple model for explaining what we call the evolution of storm tracks. So this is a synoptic chart, a weather forecast, in which you're plotting the contours here are lines of constant pressure. You've got low pressure centers, centers of high pressure. So here we have the United Kingdom, the Atlantic. And what's significant about this is that we have this trio of low pressure systems down from the bottom left going up to top center. So these are 3 vortices in the atmosphere, following on along from one another. And one of the early problems in sort of global weather forecasting was to understand why these depressions or low pressure systems tend to follow certain tracks and how those tracks evolve. Because even if you can't forecast, or you couldn't in the pre-computer days, forecast an individual storm accurately, one of the things you could do is to look more at the global picture and understand and actually compute whether these storms will sort of follow a track that in this case takes us across the Atlantic, or whether this track might be more southerly and therefore affect the weather over the UK, Scandinavia, and so on. So understanding the dynamics of these tracks, which is intimately connected with the jet stream, was an important physical problem. And you can tackle that problem using the shallow water equations and the conservation of vorticity. So we're now making the incompressibility assumption, and this was a problem studied by the meteorologist Rossby in the 1930s. So zeta is just the relative vorticity of the flow, F is the Coriolis term. The equations of motion now tell us that this sum must be a constant as you follow the fluid motion. So if we think about a rotating box of fluid, a rotating box of sort of fluid here, which is like a very simple sort of model of a depression, what we're saying is that the local vorticity zeta must always be changing in correspondence with the changes in the Coriolis parameter as this thing changes latitude. So F is a function of latitude alone. It increases as you go towards the pole. And therefore, if this sum is constant, the relative vorticity of this swirling mass of fluid must decrease to compensate for that. And this guy, Rossby, used this to explain the meandering of these depressions around the globe. So mathematically, what he did was he took the vorticity equation, the conservation of total vorticity. He then, he first of all just noticed that, of course, if F only depends on latitude, which in this case is represented by the local coordinate y, then this simplifies this equation. Remember, this is still a nonlinear equation because the vorticity is the curl of the velocity field, and the d by dt is the total derivative, so it involves the velocity. You have this nonlinear equation for the evolution of vorticity, which is now driven by the gradient of the Coriolis term alone. So it has a nonlinear differential equation to solve, and he realizes that if you look at the sort of magnitude of perturbations governed largely by pressure differences in the atmosphere, then you can learn a lot by linearizing this equation. So you assume some basic state zonal flow, and you look at the evolution of the vorticity subject to small deviations of the velocity from this zonal flow. You can assume some sort of sinusoidal departure from a constant basic state. And if you plug this assumption into a linearized problem, you get an equation for the phase speed of these waves. So these are now planetary scale waves. And the phase speed of the flow is determined by the zonal flow. The typical length scale of the cyclones, beta, which is the gradient of F. So these three key quantities determine the very largest scale weather patterns around the planet. And obviously, depending on the values of the length scale of beta of the zonal flow, C can be either positive or negative or zero. And this tells us a lot about the large scale evolution of planetary scale weather systems. So this is a plot of it's a plot of values of pressure at a certain level in the atmosphere, looking down over the North Pole. So here's Greenland, here's Russia, we've got Europe here. And what Rossby's equation tells us is the extent to which this pattern will precess to the right or to the left or remain stationary, given the physical features of the flow at that time. And this is an old one, it goes back to July 2010. But basically this ridge here, this is a ridge of high pressure, was such that this pattern was largely stationary, so things weren't sort of changing, which led to a heat wave over Russia. What we see here, though, of course, is over the Atlantic and over the UK at the time. We have this well-developed storm track, so there would have been weather systems coming into Europe, but a very different sort of pattern over Russia. And a lot can be deduced using this very sort of simple equation for large-scale vorticity and looking at the stability analysis of these large-scale atmospheric waves. And this is the sort of thing now that is regularly seen on television. They talk about the dynamics of the jet stream. This is essentially what Rossby waves are about. They tell us how the jet stream will evolve, and of course this sort of thing now even makes its sort of way onto television. People understand that if they're getting persistent types of weather, it's due to some feature of the jet stream, and this all goes back to Rossby's work. So understanding cyclones and, more importantly, weather fronts, which is the sort of particular type of weather we get with cyclones, is really important. And this is something that meteorologists have studied using the so-called semi-geostrophic equations, which was something that was talked about by Roberto D'Onofrio in his seminar in this series last month. And they are so we will be thinking about semi-geostrophic theory as an approximation to the shallow water equations, where these approximations allow us to focus on how frontal structures, which really delineate different types of weather, can be modeled from a fluid dynamical perspective. And so semi-geostrophic theory is one that is very rich in terms of its geometry, which I shall now give an overview of. It turns out that the heart of it is a Monge Ampere equation. The equations of motion can be written as a Hamiltonian system, and one uses contact geometry in an essential way to study the formation of singularities. We now know that you can combine the contact and symplectic geometry to characterize certain types of the flow in terms of Kähler structures. And this is also related to another approach to the semi-geostrophic equations using ideas from optimal mass transport and calibrated geometry, where essentially we're saying that the solutions of the semi-geostrophic equations are in some sense optimal maps, and therefore satisfy some sort of minimal surface condition when viewed from the point of view of calibrated geometry. And again, if you're interested in some of the history behind this, then back in 1996, we ran a 6-month program at the Isaac Newton Institute in Cambridge. The proceedings of this program were published in 2 volumes by Cambridge University Press, edited by myself and John Norbury. And these 2 volumes, Large Scale Atmosphere Ocean Dynamics, Volume 1 and Volume 2, can contain a lot of information, which of course some of it's been superseded and developed since then, but will provide you with some background to this body of work. So what are the semi-geostrophic equations in the context of shallow water? Well, what they are is, again, you have 3 equations: the conservation of mass, which is effectively unchanged from what we wrote down a few slides ago, and the only difference to the momentum equations is that you replace the component of the velocity, u and v, in this Lagrangian derivative with the geostrophic velocity. So this is the flow along the pressure contours. The velocity that occurs in the Lagrangian derivative is still the actual fluid velocity. But what the semi-geostrophic equations are basically saying is that you're studying the evolution of the geostrophic flow rather than the actual particle motion. And the geostrophic wind in the case of the shallow water equations can be written in terms of this pair of equations here. So that's the semi-geostrophic system. And what you can show, so by combining these three equations, then what you can show is that the following quantity, which I'll call Q, which is known as the potential vorticity, is conserved. So it satisfies d cubed by dt is 0. Now, what is Q? So Q is the ratio of the total vorticity. So you've got the part of the vorticity coming from the rotation of the planet. You've got this geostrophic now relative vorticity, and you've got this nonlinear term written in terms of this Jacobian, and it's divided by the fluid depth. This is why it's called potential vorticity. If you write down the Lagrangian for the system, you can write down the Lagrangian, and you can show that this conservation law arises via Noether's. It can be related via Noether's theorem to a particle relabeling symmetry of the fluid. But just going back, we recall here that UG and VG, the geostrophic wind, are given by the gradients of the depth of the fluid H. And therefore, what you have here is in terms of the depth of the fluid, you have some quantity F. F here, I should have said, F in this case is now treated as a constant. So we're looking at a particular latitude on the globe. F cannot vary in order for this conservation law to hold. But you have some constant F plus something that will now involve Laplacian of H plus something involving the Hessian of H. So this gives us a clue that behind this conserved quantity is some sort of Monge-Ampere structure. Well, the semi-geostrophic equations are very often studied in terms of a transformed set of coordinates, this transformation being defined here in terms of the positions of the fluid parcels and their geostrophic and the geostrophic flow. These are called geostrophic momentum coordinates and were discussed by Donofrio. The equations of motion can be written very succinctly, the momentum equations now, in terms of these coordinates. So in this coordinate system, the flow is exactly geostrophic, and the potential vorticity is nothing more than the Jacobian of the transformation between the geostrophic coordinates and the physical particle locations. And this transformation can be realized as a Legendre transformation. So if we take the depth of the fluid H and we just multiply it by two constants, the acceleration due to gravity and the Coriolis parameter, define some new variable phi, then we can add a positive definite term to phi. We call this p. And then in terms of this function p, the geostrophic coordinates are simply the gradients of p. And one can then look at a dual function, a Legendre dual function, R, a function of the geostrophic coordinates, and you have this reciprocal relation that the physical particle locations are now the gradients of the dual function. And the representation of a singular structure in semi-geostrophic flow can now be characterized in terms of a singularity in the Jacobian between the geostrophic coordinates and the physical particle locations. So if the potential vorticity vanishes or it blows up, then this can be associated with some sort of frontal structure. In terms of this dual set of coordinates, you can also think about the reciprocal of the potential vorticity, the inverse now of this transformation. Because this is a Legendre transformation, this now just becomes a Hessian operator involving the dual function R. The dual function R can be related to another dual function, capital phi, in terms of this now negative definite term. And this is really a stream function for the flow. And so the equations of motion can be written in terms of this Hamiltonian system with the potential vorticity now transported in the dual coordinates. And the Legendre transformation has been used to great effect to create a finite element numerical model used to simulate evolving semi-geostrophic flow. This was something done by a group at the UK Met Office in the 1980s and 1990s. And what you see here is the P surface evolving as a graph in over a 2D plane, a slice through the atmosphere, and it develops this crease, and the projection of this crease onto the slice would indicate the presence of a front. And so essentially what history said was, back in 1996 at the Newton program of the Lodge, Rubtsov joined us, and we were interested in understanding the role of the Monge Ampere equation in understanding the types of fluid flow we were modeling, and how clearly some features of the Monge Ampere equation were characterizing certain types of fluid motion. And what Volodya pointed out was that we could learn a lot more if we looked at this wholeheartedly from the point of view of the Monge Ampere geometry. So this, I'm sure, this is really just a revision of what Volodya said in his talk a couple of months ago. So we're now basically thinking, if we're thinking about the shallow water equations, a 2D model. So the configuration space of the fluid is some domain which we can assign local coordinates x, y to. We can then think about the cotangent bundle over R2 and assign coordinates on the bundle capital P, capital Q. And this is equipped with a standard symplectic form written in this way. Then we can introduce another two-form lowercase omega, and which takes it has this general structure. And now if we restrict to the graph of some dependent variable phi, this is a function of little x and little y, so that the coordinates on the bundle can be identified with the derivatives of phi. If we look at the pullback of lowercase omega to the graph of the gradient of phi, then what we find is that little omega vanishes on this Lagrangian submanifold, and this condition is precisely our general expression for a Monge Ampere equation. And it's Lagrangian in the sense that if we pull back capital omega to the graph of the gradient of phi, of course that vanishes too. So one can apply ideas of Monge Ampere geometry, obviously, to the semi-geostrophic equations. But before we do that, if we're considering our general Monge Ampere equation with the coefficients a through to e, then we can compute the Pfaffian of the two-form omega, and that turns out to be the usual discriminant that occurs in classifying the elliptic hyperbolic type of the underlying Monge Ampere equation. So when the Pfaffian is positive, the corresponding Monge Ampere equation is elliptic, and we can use we can use the symplectic structure and the Monge Ampere form to write down a almost complex structure, or this operator I, which is an almost complex structure when the Pfaffian is positive, and when the Pfaffian is negative, you have an almost product structure. So this is obviously where now we introduce the notion of almost scalar manifolds. And we can, so this is something that's been applied to the semi-geostrophic equations, and the ramifications of that were essentially the talk by Donofrio, and obviously how we've exploited the Monge-Ampere geometry to characterize the solutions and singularities of those equations in terms of the geometry of the Lagrangian submanifolds, the graphs of the gradient of the stream function P or phi. But we can also apply this, and this is now a separate bit of work. So this is no longer connected with semi-geostrophic theory per se, but one can do this for 2D incompressible flow. So this is just now going back to 2D Euler, where vorticity is transported with the flow, and the Poisson equation for the pressure, which involves the Hessian of the stream function. This can be written in terms of a Monge-Ampere form of a particular simple type now. So we just have this coefficient. We're treating Laplacian of pressure as a given function, and we'll be interested in the case where you restrict u and v to be the gradients of the stream function, and you restrict this to the graph of the gradient of the stream function, and one can just go through the mechanics of the Monge-Ampere geometry, write down an almost complex structure, and now what you find is that when Laplacian of pressure is positive, you have an almost complex structure. The Monge-Ampere equation for the stream function is elliptic. When Laplacian of pressure is negative, it's hyperbolic, and of course ellipticity means vorticity is dominating over strain. Hyperbolicity means strain is dominating over vorticity. So the regions of the flow which you might want to call a vortex, as defined by Laplacian of pressure being positive, are now characterized by the existence of an almost complex structure, those that are hyperbolic and almost product structure. Integrability, imposing integrability is quite a severe constraint in this setting. It really means that you're looking at flows where Laplacian of pressure would be uniform, which you can do in very simple vortex structures such as Rankine vortex, but obviously in 2D turbulence, the Laplacian of pressure will be varying from location to location and with time. So time is a parameter in all this. And so one is typically dealing with instances where these structures aren't integrable in this sense. And as I've just mentioned, time is a parameter in all this. And therefore, the Laplacian of pressure evolves with time. What we've just seen is that the Laplacian of pressure is effectively the Pfaffian. It's also related to the second invariant of the velocity gradient tensor. And you can write down an equation for the evolution, because it depends on time. You can write down an equation for the evolution of the Pfaffian. And what turns out to be interesting is that the evolution of this geometrically significant quantity is now crucially dependent on inhomogeneity and anisotropy in the pressure field and in the stream function. So the box operator here is just the wave operator, and we see the cross derivative terms of the pressure field and the stream function occurring. So it's the interaction of inhomogeneity and anisotropy in the fluid flow that drive the evolution of the Pfaffian. Which potentially means that what Monge-Ampere geometry is focusing on in this context is the very types of flow that are crucially important in developing turbulence. Typically, when these terms are zero, it's very boring, and you have canonical vortex structures, but not much else is changing. So potentially Monge-Ampere geometry in this context is now something that takes us into the realm of being able to study turbulent flows from this sort of novel geometric view. And more recently, what we've done more recently, and this will be something that hopefully our student Lewis Napper and work in collaboration with Martin Wolf at Surrey and Blodgett Rubtsov will be able to say in perhaps later seminars in this series, is that, of course, what comes along with the Monge-Ampere geometry is a natural metric. First of all, a metric on the cotangent bundle, which can be computed from a formula such as this, using the Monge-Ampere form and the symplectic structure. But one can also look at the and what this metric then tells you, first of all, is the signature of the metric typically changes between the elliptic and hyperbolic characters of the Monge-Ampere equation. So if you have a Monge-Ampere equation with non-constant variable coefficients, so that you have a problem which is elliptic in one region, hyperbolic in another, then typically you have a metric which changes signature. But one can also look at this metric, one can look at its pullback to the Lagrangian submanifold defined by the vanishing of the symplectic structure in the Monge-Ampere form. And our most recent work is now sort of showing us how the induced geometry, the geometry induced by this metric on this Lagrangian submanifold, can tell us about topologically distinct characteristics of the underlying fluid flow. So this is quite an exciting new development, and I will leave the technical details of that to few future talks. But hopefully this gives you an idea of where this, what is motivating this work, and why we're quite excited about potentially its applications in studying turbulent flows. And this is really this was really brought together in a statement by John Gibbon. This was in a paper published in Physica in 2008, which was the proceedings of a conference celebrating the 250 years of Euler writing down his key equations of fluid motion. And Gibbon really highlights the role of this relationship between Laplacian of pressure and Vortistian strain, and it's worth just repeating this verbatim, because he says this elliptic equation for the pressure. So typically this is an equation which you might use to find the pressure rather than using it to determine characteristics of the flow via Vortistian strain. But he says, this equation for the pressure is by no means fully understood. And locally, it holds the key to the formation of vortical structures through the sign of its Laplacian, so through the dominating influences of vorticity over strain. And it's in this relation, which is often regarded as a constraint, may lie a deeper knowledge of the geometry of both the Euler and Navier-Stokes equations. The fact that vortex structures are dynamically favored may be explained by inherent geometrical properties of the Euler equations, but little is known about these features. And really what we're trying to do now is to sort of take this statement and really put it under the microscope using the ideas of Monge-Ampere geometry, and more recently what the Monge-Ampere geometry on the cotangent bundle starts to tell us about the geometry of the Lagrangian submanifolds defined by the vanishing of these Monge-Ampere forms. And a recent paper makes some progress with this. So I'm going to now draw things to a close. I hope you've enjoyed a bit of a rapid tour through some of the history of this subject. What are the two key takeaway messages? The two key takeaway messages from my point of view is that geometry quantifies qualitatively important characteristics of fluid flow. So what's really important if you're an oceanographer, a meteorologist, is that you identify features of fluid motion that you have to focus on, So we know from a qualitative level that these are important in determining large-scale weather patterns. What geometry does is give us a way of quantifying this through things like studying the importance, the central role of the Monge-Ampere equation, and how that itself governs the sort of the dynamics of the flow through the solutions that are possible in that system. And also that topologically distinct flow regimes can be described in terms of the geometry of Lagrangian submanifolds within the broader context of Monge-Ampere geometry. The ideas originate in the semi-geostrophic model of atmospheric flows. I haven't had time to talk about the early work that I did with Volodya, a couple of papers in the late 1990s to 2000s, looking at the semi-geostrophic equations from the point of view of Kähler geometry, which was further developed by a student, Sylvain de Delahaye, with me at Surrey later on. And this really, it shows us how Monge-Ampere geometry gives us an overarching framework for studying things like solutions and singularities of the equations. And I'm sure you learned a lot about that from Donofrio's talk. And we now know how to interpret the so-called Weiss criteria in turbulence in terms of geometry. Back in 2009, in a paper with John Gibbon of Volodya and Bertrand Papanos, we showed how we could take some of Nigel Hitchens' ideas on the geometry of three forms in 6 dimensions to generalize the Weiss criteria to, or generalize the geometric version of the Weiss criteria to 3D incompressible flow. And here's some references to some of the more recent work we've been doing. There was a symposium in Wisła in Poland in 2018, which Volodya, Martin Wolf and I participated, and some of the proceedings have been written up, published by Springer, and there's a paper in there by Bertrand, Volodya and myself on the geometry of meteorological models from the point of view of Monge-Ampere. More recently, we've had this paper published in Proceedings of the Royal Society early this year, which comes out of the PhD work of Roberto, co-authored with Giovanni Ortenzi in Milan, on the solutions and singularities of the semi-geostrophic equations by the geometry of Lagrangian submanifolds. Finally, Roberto has published a very nice paper in Journal of Geometry and Physics, which points out an important connection between the theory of optimal transport and the Monge-Ampere geometry, using semi-geostrophic theory as an example. And I think this is a very intriguing and a very promising link between two very important bodies of work, the application of optimal transport and the application of Monge-Ampere geometry, and what Roberto has done in this paper is to connect the two. And then finally, the more recent work we've done, really studying the role of these Lagrangian submanifolds and what they can tell us about the phenomenology of fluid flow, is now written up in a paper that's available on the archive by Lewis Napper, myself, Volodya and Martin, on Monge-Ampere geometry and vortices, which really sort of puts a lot of these things, as I say, under the microscope. And so with that, I haven't quite filled out an hour and a half, but I will finish there. Thank you.
Thank you. It's very interesting talk. So any questions, any comments? Volodya, maybe you?
Well, I want just to say that thanks a lot, Ian, for beautiful talk and for this story. I would add just a small, I think, important thing, that in '96, during this Cambridge program which Ian and John Norbury organized. It was a small 2 weeks parallel program which was organized by Sir Michael Atiyah. It was his last month of directorship in this Newton Institute. And he organized a workshop in geometry and instantons, and it was plenty star talks. There were plenty star talks there. And during one talk, it was written talk, I had no place in the main hall, and I found a person who also had no place in main hall. It was Nigel Hitchin. We discussed with him maybe 1 hour and a half, and then next day again 1 hour and a half, and then Nigel just understood probably that it is useful to mix persons from different programs in the same time in this, and he told to Sir Michael, you see, there are people from the parallel program who attend our program, and they speak something interesting. So it was the first contact with geometers in Oxford, and then Ian continued these contacts. In particular, I think that appearance Martin Wolf in our group, it's a part of long-standing cooperation with geometers of Oxford.
Thank you. Any other comments, questions? Okay, maybe